Hello all. Welcome to this new episode of QWave, the fourth one. Today we will be listening to Johanna Sepulveda from AIRBUS about the new era of secure communications and some insights from the industry and that kind of things. So we will explore the quantum secure communications, their global status, the and large scale deployments, like for example EuroQCI and these kind of things, and highlighting their transformative impact on critical sectors, and of course the future market opportunities. But before starting with QWave, I want to introduce a little bit of quick for those who aren't familiar and just jump into this webinar in YouTube. So what is QUIC? So QUIC is a non-profit association established back in 2021. And our mission is to grow and strengthen the quantum technology industry, I repeat, industry, because we are an industry-led association, and position Europe as a global leader of the sector. Here you have a QR code that you can scan that leads to our website where you can find more information ourselves about our different working groups, activities, and different white papers and publications that we have. Also, I want to talk about QExpo. QExpo is the expo that QUIC is part of, is a leading part of. It's going to be in May on the 14th and 15th in Amsterdam. And we'll have one day for the industry exhibit, and the second day will be a plenary day. You also have here the QR code, and the website is qexpo.org. The registration is open, so you can just register yourself. And also, we still have some booths and sponsorship opportunities, so feel free to go to the sponsorship tab and find if you're interested in. Well, with giving that said, I'm going to introduce our speaker of today's session, that is Johanna. So Johanna is a leading expert in quantum technologies and cybersecurity. She holds a degree in electrical engineering from the National University of Colombia, and a master's and a PhD in electrical engineering with a specialization in microelectronics from the University of São Paulo in Brazil. Through her career, she has worked as a senior researcher in security and emerging technologies at institutions such as the INRIAD in France, as well as the Technical University of Munich in Germany. She also participates in different standards bodies, and currently she serves as a senior expert in secure quantum technologies at Airbus Defence and Space. She also works and leads European initiatives, including the European Quantum Communication Infrastructure, EuroQCI, or the acronym, and she is also vice chair of the European Commission's Strategy Advisory Board of Quantum Technologies. She has more than 15 years of experience in research and development in security, in systems, high-performance computing, and quantum technologies. So given that said, I let the floor to her to show us the slides and start the speaking session.
Thank you so much. Good afternoon, and it is a pleasure to be here and to and to be. We are as AIRBUS, we are very proud to be part of QUIC. So, with pleasure, we are going to go and show the slides and discuss about the next era of secure communications. So, thank you so much for the introduction. So, let's start with which is the motive of, or the reason of caring about and designing the next generation of quantum of secure communications. So there are several threats that are ongoing and that somehow jeopardizing the secure communication. And one of these is the quantum computer. So quantum computers, they have received huge investments across all Europe because they are these kind of special machines that relies on quantum physics and that are able to overcome the speed of the current supercomputers. So for what we use the quantum computers? So these kind of computers, we use it for certain applications. So it's not a general purpose machine. And we use it for three main applications. The first one is for modeling complex systems. So this kind of machine can overcome the current limitations that the time that is required to modeling the system with the traditional HPC capabilities. The second application, it is the optimization of hard problems. And the third is security. So with these kind of machines, it is able to break the public key cryptography that currently is used for key exchange, signatures, for example, and as well, it will jeopardize or impact the symmetric cryptography by halving the security level of the current symmetric cryptography. So these, in order to do that, these machines have to have relative high computational power, and it is foreseen that this kind of machines able to break the security will arrive at any moment in the next 10 years. So let's understand what we care today. So currently, the cryptography, the traditional cryptography, is considered secure because even with all our computational power, it will require 17 trillions of years or many years in order to solve the hard mathematical problems that we use to secure our communication. Nevertheless, that is not the case with the quantum computers because they are able to execute two quantum algorithms that we know now, that is the Grover algorithm and the Shor algorithm. The Grover algorithm will impact the security of the symmetric cryptography by halving the security level of the cryptography. Fortunately, for the symmetric crypto, there is some ways to patch this kind of mathematical systems in order to continue being secure in the quantum world. And for that, the symmetric cryptography can be the key of the symmetric cryptography can be double, and then it is patchable. But that is not the case for the public key cryptography. So with the public key cryptography, that is very relevant, as I mentioned before, for key exchange, for signature. It is the execution of the Shor algorithm in the quantum computers will cause that the public key cryptography is broken. So we need new kind of capabilities to ensure security. And we see nowadays that there is different security challenges. We have seen different attacks with the traditional cryptography, as well as different initiatives of further speeding up the development and the use of these quantum computers for breaking the security. So that is why it is required to think on this technology now. But why now? So we have different applications that are characterized by different life cycles, as shown in the picture. It is foreseen that as I mentioned, that these quantum computers will arrive in the next 10 years with the capability of breaking the security. That means that we will need to make a transition towards quantum secure mechanisms. But during this transition, it is really a process that will require some time. So during all this transition, the different assets or the different applications will be exposed to attacks. In addition, an attacker today can record the secure information and store it into a memory and decrypt it later with a quantum computer. So that is why it is very relevant to consider the protection against this quantum threat now. And this kind of protection or this kind of migration in order to cope with the crypto obsolescence will present different risks, but also opportunities. The migration towards quantum secure mechanisms, it was also already advised by national security agencies already in 2016. And from that time on, different organizations, governments start to look at the transition and migration into quantum secure mechanisms. So currently, there are two technologies that are considered quantum secure. So the first one we can talk about is the quantum communication, providing different services like the quantum key distribution. And the second is the post-quantum cryptography. So the quantum key distribution, it uses the principles of the quantum mechanics in order to create quantum channels that enable the transfer of a secret key. This key that later on can be used, for example, with an symmetric cryptography, AES-256, and can enable the end-to-end communication, secure communication. So, but why these quantum channels are considered secure? They are considered secure because the quantum has very important properties. So, first of all, the quantum information cannot be copied. And second, any eavesdrop will be detected. So, these properties are very interesting for building secure systems. The second alternative is the post-quantum cryptography, that it consists in different mathematical problems that are considered hard to solve with current computers and with quantum computers, as far as we know, and that can protect, they can be integrated into protocols and can protect the channels. These algorithms can already be implemented into our normal or traditional technology in order to do so. What is very relevant to mention is that these two technologies are not competing together. These are two different security technologies with properties to cope the requirements of different applications. In addition, it is expected that the transition for this traditional world to a quantum secure world, it is performed in a layered way. So that means where we have a traditional cryptography, on top we will have a post-quantum crypto, and for certain applications that require high level of security, that like for example, critical infrastructures, healthcare, governmental, etc., financial, they might have an additional layer with a quantum communication. So again, these technologies do not compete, but are part of the quantum secure landscape. So let's look about to the post-quantum cryptography and the lessons learned that from the quantum communication we can have. So first of all is the diversity. Post-quantum cryptography it includes 5 different families of of problems that are considered hard to solve with current computers and with quantum computers. These are the code-based, the hash-based, multivariate, isogeny, and lattice-based families. Or each one of these families have different advantages and disadvantages. So that means that they are not an optimal one. So, for example, the code base, it is based on well-studied error correcting problems. They already were proposed in the 70s. It is multi-purpose. So what does it mean? That means that it can encrypt, decrypt, sign, and verify information. And it's considered fast. Nevertheless, the disadvantage is that it has big key sizes, large key sizes, which somehow have an impact in the bandwidth of the communication channels, as well as in the execution of the secure capabilities. The second family is the hash base, that is also relies on different hash functions. We like hashes in the sense that we know how to use it, all the security properties. Many of our processors even, they have already special pieces of hardware to further speed up these hashes, and they are considered very efficient. Nevertheless, with this kind of family, we only can sign and verify information. We cannot encrypt on the crypt. And also, if we require the drag of some message, so sometimes the implementation also is a bit tricky. In the multivariate, the advantage is that it's multi-purpose, so you can assign, verify, encrypt, decrypt, and also have very efficient signature scheme. Nevertheless, many of the proposals based on this family has been broken. So the reliability or the trust on this kind of algorithms is very low in this kind of family multivariate. Then we go to isogenies. Isogenies are based on elliptic curves. So usually cryptographers like that very much, and engineers, because we know how to implement it in a secure way. Also, the elliptic curves. Also, there are different kind of processors that already have some pieces of hardware to further accelerate this. So some coprocessors just for this kind of elliptic curves of operations, and it has a small key sizes. But the problem is that it has a low efficiency. It is difficult to construct, and also they have been attacked. And finally, the lattice-based cryptography, that it is considered very efficient. Also, it is used for multi-purpose secure application. That means encrypt, decrypt, sign, verify, and even we can build very complex crypto primitives with them, like fully homomorphic encryption, identity-based encryption, etc. Nevertheless, when compared to traditional cryptography, the key sizes are still large. So just that you know, the post-quantum crypto was subject of a very strong and very wide standardization effort. And currently, the algorithms from the family of the hashes and lattice base have been standardized at NIST. I'm going to further talk about that. But also other associations and other standardization bodies are looking for code-based crypto, so that in the future we might have code-based standardized as well. Second, lessons learned that we can learn or that we can have from the post-quantum cryptography is the formalization and the capability, for example, to define different levels of security and different compromises in terms to create crypto primitives that can be tuned, or that they have some family of parameters that have been studied in order to have different compromises of security, performance, compatibility, etc. So the formalization for the quantum secure world, it is very relevant, and to have or to be able to measure or to express different security levels is also relevant, and to tune parameters so that we can have this kind of compromises between different KPIs is also relevant. So it is a second lesson learned that we can that we from the quantum communication work can learn from the post-quantum crypto. Now it is the part of the roadmap of the different of the standardization. So the standardization process it was a process that was run by the National Institutes of Standard and Technology, NIST, in which they, with all the community, they were receiving different algorithms with post-quantum properties that belong to these families. And what it was done, it was organized like a contest in a round basis in which the algorithms were evaluated and studied by all the community. And where at each round they were performed a down selection of algorithms. So to have several eyes looking at the security properties, it is very attractive. So currently, what we have is like last year, the publication of the standard was launched. And so it was released, and now we have algorithms for lattice-based and hash-based that has been standardized. We have one key exchange that is Kyber Lithium, and we have three different signatures when it was already published specifications and the standard for the dilithium signature, as well as for the Sphinx, the hash-based signature. Okay. So it was a process. During all this process, AIRBUS also have been pioneer of the integration and exploration of this post-quantum cryptography into different applications. So we already start since 2017 in order to further implement or explore the capabilities of these algorithms, as well as the implementation in different platforms, from IoT to some capabilities used for wireless sensor networks, up to different powerful processors. So AIRBUS has been pioneer also in the part of the co-design and crypto agility of post-quantum, in where we design hardware and software pieces that enable and give some flexibility to change these crypto capabilities. Also, AIRBUS was the designer of the first European chip with post-quantum capabilities to further explore the speed up and of these algorithms. And we have made different demonstrations of the integration of these algorithms into protocols for securing different applications, such as drones. We are also exploring the securization of space with post-quantum crypto, etc. So, as a summary, what we can learn from all this process that it is carried out in the quantum world, in the post-quantum world. So we see that the technology adoptions needs some time, and that the standards play a very important and relevant role. Also, it is important to involve all the stakeholders and the community. So, and more in this topic, it is characterized by a multi-domain ecosystem, including cryptographers, engineers, the applications, and the users of these secure capabilities. Also, it was relevant involvement of the different regulation bodies, like national security agencies, governments, and this process was very open and participative. Understanding, being able to formalize properties is also important. So it is the physics also can be formalized into mathematics. So it is also important to have this kind of formalization. And the focus is on the security and use cases. Remember that these technologies are used for the securization, for the protection of the information. And that should be the goal. So now let's talk about the quantum communication that you were waiting so much. So as I mentioned before, these quantum communications are enable the secure exchange of secret keys now, and in the future will enable also the interaction of different quantum assets and different devices. So evolving in something that it is called by some persons like quantum internet. So these quantum links can be spanned across a network that it is deployed in the terrestrial and space segment. Each one of these segments will have different advantages and disadvantages. In the terrestrial part, it can be used optical fiber or free space, ground-to-ground optical links. The advantage of this kind of terrestrial segment is the high throughput when compared to space, for example. Nevertheless, it has currently a limited coverage. Why? Because currently we have, in order to build these networks, the maximum distance between consecutive nodes will depend on the losses of the fiber, and currently it is about 150 kilometers where these consecutive nodes in the terrestrial segment can be located. Now, talking in the space, so the space offers a wide variety of opportunities. These space links use free space satellite links, and they can offer a wide coverage. Nevertheless, they suffer for some low throughput that can be affected by different environmental conditions, such as weather, such as pollution, etc. This kind of technology is not just some theory. It has been already demonstrated across the world. So in the terrestrial segment, the demonstrations have been done since 2002 already in DARPA. It was in 2008 when the European Commission support our.
Sorry, Joanna. We are currently looking at the slides of NIST security levels. I don't know if you have mixed some slides or.
No, I already am in other. I am. Oh my God. I already are passing several slides. Let me see what happened. Can you see the slides?
Yeah, yeah,
Okay, I'm going to try to show again, and then can you see the move of the slide?
yeah.
Okay, good, great. So I'm going to. That's unfortunate. Anyway, just showing here the roadmap that I was talking about
Okay.
the post-quantum crypto, together with the AIRBUS footprints, where you can see the different kind of demonstration and initiative that we have, and how we were contributing into the development and integration of post-quantum into applications. Here highlighting the design of the first European chip in Europe with post-quantum capabilities. And the different kind of applications and demonstrations, such as the demonstration with the drones, swarm of drones in the space as well, etc. Then some of the summary of the lessons learned we already mentioned. So it is something that we can get in order to further advance in the quantum secure area. And then we go to the communication. As I mentioned, we have different kind of segments, terrestrial space, each one with advantages and disadvantages. In the terrestrial part, I was discussing about that there are already demonstrations, so it's something and also there are several networks that already are in operation with customers. So it is something that is not just in theory, or it is something that is just more for the the academic world. It's something that is really going through a market, through an industry. So the first demonstration that I was performed in Europe was under the umbrella of the project EuroQCI in 2008, in which different partners joined to make a six trusted node network in the terrestrial segment. Some of these partners were later on hired in Tokyo, so that they can build this network with the novelty that for the first time it was just not the physical world, but also with a key management world, enable the controllability of the life cycle of these keys. Then we have South Korea, how it is advancing in this kind of network. There are already customers that are already using this network for different commercial purpose. We have the Italian backbone demonstrated in 2018, that is the largest backbone in Europe. In Cambridge, they have been several demonstrations of quantum networks achieving records of performance. And we have also the first demonstration in cross-border with different countries performed in between Italy, Slovenia, and Croatia in 2021. Also, later on, I'm going to discuss about the EuroQCI initiatives and all that currently Europe is doing regarding further developing this technology. For before we pass to the space, I have to say that for far, the most advanced quantum network that we know today is the Chinese network, which already have some terrestrial and space segment working, and with the capability of connecting all different sites in China with different customers. Which are these customers? Critical infrastructure, governmental, financial, and healthcare segment. So in the space also, there have been several demonstrators in which a payload enhanced with quantum capabilities have been flight in different orbits. We have that QKD and quantum links already in embedded into kites, into aircrafts, but also in satellites that are that are located in the LEO orbit or low Earth orbit, in the medium orbit, and many countries also have been announced their ambitions to go for the GEO orbit integration of these capabilities. Here, I also highlight the role of AIRBUS, and also where in 2019 and under the project Kudos in the UK, we demonstrate the integration of QKD capabilities into drones. And in the future, it is expected that we can also might include these capabilities into some hubs of pseudo satellites and also drones, and also to including underwater for creating underwater links with these quantum secure capabilities. This is the state-of-the-art network of China. You can see how it is spanning across all the territory. It has more than 30 trusted nodes in the terrestrial segment, plus the part of the space. And here, what you can see are the different customers that are linked to this network. But one thing that is very relevant to mention is that quantum networks is not only the quantum layer. The quantum layer is very important because it integrates the different devices and the different elements that allow to build this quantum link. But in order that we can provide a service between end to end, providing services to the different users, it is relevant to take into account that there are many building blocks that must be built and designed in order to enable this interoperability, this integration of these new capabilities to the secure communication area. These building blocks also must be developed in a secure way so that it is possible to provide the end-to-end service. So Europe, of course, is very concerned about this threat, and also wants to deploy the quantum network covering and protecting all the European assets. And it is what is called the EuroQCI, or the European Quantum Communication Infrastructure. This was a program that appeared from an agreement for the different member states in Europe in order to build these quantum networks that span across the terrestrial and space segment to cover, to protect European assets inland and overseas. In order to do that, the European Commission
Sorry, we are looking at the worldwide demonstration slide. This one. Can you share it again?
Yes, it is. Can you see it?
No, right now.
Okay. Again, can you see it?
Now we can see like the worldwide demonstration of space.
Space, exactly. So that is what I mentioned about the orbits. Could you please let me know if the slides are not changing? When I change, I will just say
Yeah.
I'm going to change the slide, and then Otherwise, we
Yeah,
miss the thing. Thank you so much.
no worries.
Okay, perfect. So that it was the different demonstration of space and in the different orbits that I was discussing about. Then in the next slide, it is how we can look in the future. And here we can see different hubs of pseudo satellites that can, or maybe in the future, can integrate these quantum capabilities in order to enhance the service provision to different areas and to different customers, or in drones as well. And the next slide, here I'm showing the Chinese network that I have talked about that span across the terrestrial and space segment with more than 30 trusted nodes. And what it is interesting, as you can see there, it is to identify the different customers and that are already integrated or are already using this network. And that means the governmental, critical infrastructures, as well as the healthcare organizations. So these are the trusted nodes. Then we go to the next slide, and here I'm discussing about the relevance of the quantum layer, but also that the quantum layer per se alone doesn't make a network, doesn't make a system. In order that we can have this system able to provide secure keys in a secure way, keys from for different users, and in the future also, instead of keys, data or quantum data, also giving the given the opportunity of the quantum internet, it is required to build several building blocks or several blocks that are required for the interoperability, for the integration of this quantum layer to secure communication, to a communication infrastructure. So that is very relevant. In the next slide, what I'm showing is the roadmap of the EuroQCI. So as I mentioned before, it was the European Quantum Communication Infrastructure, this program that appears in 2019 with the interest of the different member states in order to build a network that spans across the terrestrial and space segment to protect the different European assets inland and overseas. In order to do so, that the European Commission has financed different kind of projects that enable the exploration of
The
the.
slide move.
In which are we?
Now we are in the, no, that's the roadmap of EuroQCI right now.
Yes, correct. Yeah.
Okay.
So we are in the with different programs and different projects that allow not only the exploration of the technology, but also the design of the end-to-end architecture, the deployments at different and all the different member states of Europe, as well as the secure evaluation. As I mentioned before, in the terrestrial and space segment, where they are working very close with with ESA, the European Space Agency. So, in order to build this network, AIRBUS has contributed to and has a leader role in the system design activities, in where AIRBUS is the designer of the Euro end-to-end EuroQCI. And also, our colleagues of space, they are designing the backbone of the space that is called, in the context of this project, that is called SAGA, as well as the design and integration of the optical ground station that are in the terrestrial part and are able to receive these and communicate with the satellites. So that is what we are doing. And in addition, it is foreseen that this EuroQCI, it is also integrated into the IRIS Square in the future. As I mentioned before, since already 2 years ago, the different member states of Europe are deploying national networks, and it is expected that these national networks can be linked later on so that they can build or they constitute the EuroQCI. In addition, also there are different segments that are also looking at the quantum communication, and that includes the defense part. So currently defense, and it is also investing in designing end-to-end networks with quantum communication for the military environment, and AIRBUS is working on this project together with partners, the project called Anchor, that is supported by the EDA, or European Defence Agency. So one important remark is that how this kind of like Euro QCI can look like. So as we see, we have a network of networks where different nations will define and they have the sovereignty to define and decide how will be the architecture of the network. What it is important is to define how these different networks will interoperate or will communicate. When discussing or thinking this network, it is very important to think of the different security level and the relevance of the interoperability, not only between the national domains, but also between the terrestrial and space segment. So one thing that is relevant and that is the goal is that the interoperability should be achieved in this regard with the different national decisions and architectural choices. There should be a way that these networks can exist and communicate. So for that, there have been discussed different kind of approaches. When we talk about the interoperability, when we think just purely on the technical side, one link-to-link communication can be only be performed if these boxes are compatible, and usually they belong to the same vendor, and they have also the same version in a firmware. So this might be a challenge when we talk in the cross-border or between countries connection, because as I mentioned before, each nation it has the independence to select which are the vendors and providers they use. So one approach is to use border gateways. So it is a third party that will enable this communication between different domains. So from the point of view of the technical point of view, just quantum point of view, it might be possible to use a border gateway in order to link two different nations with two different suppliers. Now, for the security point of view, this link-to-link connection, as it is making into this figure, it can only be achieved if there is a trust between the two domains, and there might be not a realistic scenario. So again, from the point of view of security, it might be interesting to use a border gateway that enable this communication between the different parties, and it acts like a trusted third party. But as we know, trust is a concept that is very complex, and the trust is not unique. So it must be that in the future we have different trusted third parties that will enable and will facilitate this interoperability between the different national networks. And how this will be done, how this interoperability will work. So it is something that currently it is under discussion in the European Commission, involving different stakeholders, not only for the regulatory security, for different domains of expertise, so that this can be further clarified and interoperability is possible, and we can see soon an EuroQCI in Europe. And with that, I finish my presentation. Thank you so much.
Thank you, Joanna. Uh, really insightful. A lot of things are being done in the realm of communications and the different quantum, classical, the networks and everything are, I think this is amazing. So let's open the Q&A session. So I have seen some questions in the chat, so I will start for the ones in the chat, and if there is no more questions, I will ask because I have some of them. So first of all, Thierry asks, what is the level of awareness and appetite from Airbus customers for quantum secure comms? Are they today ready to transition to quantum secure comms?
So quantum secure transition, it is a must, and our customers know that it is a must. So they already are working together with us in order to make this transition. One thing that I want to highlight is that when we talk about Airbus customers, we are talking a wide variety of stakeholders, because Airbus, we have different products and services. So currently we have the part of aircraft, commercial, and for that, for example, we work with the airlines in order to for the because we also provide services in order to make these quantum secure capabilities. We have helicopters. These helicopters also they have different crypto capabilities that sometimes even they are tuned to the country in where they are set. And we are also working already with our customer in order to enable this transition. For sure, the first layer will be like the post-quantum crypto. That is something that is for now. And currently, more and more, we are receiving the interest of the quantum secure communication based on quantum links. And one example is that in the Airbus defense and space part, that includes air power with all the aircrafts and drones. For military environment, we have space with the satellites, optical ground station, and we have the connected intelligence. We in aerial defense and space, we are working with, for example, the European defense agencies, with different minister of defense, exploring this technology. And one example is the project Anchor, in which currently, together with some countries, we are exploring the end-to-end design of these military networks.
Yeah, indeed, we believe that there is a need for this transition, but let's see how it becomes and how the different agencies and bodies PAs to do so. We have another question in the chat talking about that if airplanes do use quantum communications, he will think that there must be some global standards being discussed for the issue in the industry. And if are there any standard setting initiatives known to be underway?
Thank you so much, Ariel. Indeed, the standardization is very important as well as certification. And it's not only in the airplanes and aerospace industries, but in the wide telecom industry in general. So currently, there are different standardization bodies in which they are discussing and already publishing standards recommendations that include, for example, the ITU, that is more a very international standardization body. Also the ETSI, that is more European, but also where the different companies across the world sit there to discuss this body. In the European level, also we have Sense and Elect, where they have special branches to discuss about quantum, and not only quantum communication, but also quantum computing, quantum sensing, etc. So for sure, it is very relevant, the standardization, mostly if we want, for example, to achieve this interoperability. And in addition, for example, to whatever we put in an aircraft, we need also certifications. So certification also will be required if we want to put something in the or modify something in the aircraft. So that is something that we are working together with the community and also other industries that are we all will be influenced by this kind of transition of move of secure paradigm.
Yeah, I feel it's really important, and also we from Quick we have several working groups. One working group is focusing on GTC 22 from Sentinel Lake, and another one about international standards. So we fully support standardization, and we think it's really important. Yeah, more questions. So Carlos Funod asks, what is in your view on what is your view of the QKD equipment market in Europe, and what is needed for it to exploit?
So currently, and we know that with the initiative of EuroQCI, this has really fostered the development of European equipment, and mostly in the area in the different branches, quantum sensing, but also in the part of quantum secure communication. We have seen how different the innovation and the different ideas that were born in some universities, now they are becoming in spin-offs that currently are even being acquired by big companies. So they are being very successful currently. So I think the level of innovation and quality of the European know-how and equipment, it is very high. Currently, it is further being developed and tailored to cope with this EuroQCI capabilities. All these providers must be also further be supported, because currently it is clear that there is not a market, a wide market for the QKD. So it is very relevant that it is created a healthy business ecosystem so that they continue being producing and providing the high quality that they have. So for that, we need the support of Europe to create this healthy ecosystem, and they can continue developing the technology. But I can, and I just am going to make some advertisement of some of the brands because I think they deserve. They have worked a lot. And here I can mention even Quick. They are Quick members, and I can mention Lux Quanta. I can mention Think Quantum. I can mention QTI, acquired now by Team Group. I can mention Jena Optics, and some of them. The others, please, sorry if I don't remember, but they are doing excellent. Aurea, they are making excellent job. And I really invite everybody to go to the Quick site and look to all these SMEs that are already in Quick, further discussing different topics like standardization that we talk about, how to create market opportunities. So it is a good arena to work together and to continue growing these capabilities in Europe.
Yeah, I agree. And if you have more questions about Quick, our members, memberships, or whichever, feel free to contact us. There are more questions in the chat, but I want to ask one as they are talking about the QKD landscape within Europe. And my question is that what do you think are the critical or the biggest challenges in deploying large-scale quantum communication infrastructure? Like not only for Europe, like actual international or beyond the borders.
Yeah. So currently, I think that is something that will boost the market. It really needs this formalization. Because if we have this understanding of all the security, the security capabilities, limitation of these technologies, it will be embraced by the different customers. This is relevant. This is one point. The second point is the interoperability. So we need to create ways to enable the interoperability, to make possible to interoperate between different vendors, etc. So standards also are relevant.
Yeah, and I have seen another question. I don't know if it's suitable, but As the technology matures, is Airbus planning to increase the investment in the next year? And I will like revamp the question. It's not only about Airbus. What's your opinion about the investment? And I believe it's the technology is being mature. Uh, how do you see that landscape of investment in general and in Europe or
So currently, what we see in the worldwide is that the investment are increasing, in the sense that it is seen how the advancement of the quantum computers can thread the communication. So that is why a migration is not a choice; it is a must. So we have to migrate. Yes, the first part will be the post quantum crypto, and that is why we need certified products, certified services with these kind of capabilities, but we also will need quantum secure capabilities, the quantum communication, excuse me, in the terrestrial and space segment. So this will increase and is increasing, but will increase more when we can have the certification of products, because then it will be something that can be used. That is why it's very important, for example, initiatives like the BSI certification of the smart card with post-quantum, or the protection profile that the BSI together with ETSI, they develop, and it is like a former a big step towards the big adoption of this technology.
okay? So thank you so much, and thank you for being here explaining quantum communication and the difference and what is Airbus doing towards that. Also the different bodies and European efforts, and also thanks to the people here. I will wrap up and also share with you some information about QWave. You may have seen that we have changed a little bit about the coloring. We are working towards making this QWave Webinar Series a cool thing. So also remember to follow us in LinkedIn, to subscribe to our YouTube channel, and be informed about the next QWave series. So we are planning to have this kind of series on the third Friday of the month. So expect to have another one on the 21st of March. And given that said, I want to thank you again, Joanna, for your talk. I believe it's something important and really interesting. And thank you all for being here.
Thank you for